If you remember, towards the end of Chapter 17, we began discussing equilibrium states that result after a chemical reaction has occurred, not just a dissociation. Problems that exemplify this look like this. Okay. Calculate the hydronium ion concentration and the pH of a solution that results when 22 milliliters of acetic acid is mixed with 22 milliliters of sodium hydroxide. These represented situations in which equal amounts of a weak substance, in this particular case it's a weak acid, was mixed with a strong substance, in this case a strong base. In the new chapter, we'll be doing some more exploration as to how this type of situation is handled in other types of reactions. I'd actually like to begin by working through a problem. Okay, so here we have what is the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make a 1 liter solution. First of all, when looking at this problem, it is important to note that the ultimate goal, the final answer, will be a pH, just like we've been doing. So just like normal, your first question should be, where do the H plus ions come from? Also like normal, they come from the acid and the water, but the water, of course, isn't a significant source of H plus, so we kind of ignore it. So let's focus the problem on the most important source of H+, which is going to be the acetic acid. So let's start off by writing that chemical equation. Okay, you can see it written up here, and you can see that I've already sort of set up the icebox below. Okay, the next step is to start filling in our icebox. So initially, you can tell from the problem that you have 0.3. They told you it's a 0.3 molar solution of acetic acid, 0.3 moles in 1 liter. And we know we can ignore our water. Okay, so I'm just going to put lines through that. Okay. The difference between this problem and previous problems is that there's now a new source of the acetate ion. Okay. So this acetate ion right here, which appears right here as well, also comes from the sodium acetate, which was added in the original problem. Okay, so we're told that we have some sodium acetate, which is going to dissociate in water, and realistically, that's going to contribute some more of this ion right here. Okay, so that tells us that instead of having an initial concentration of 0, we're going to have an initial concentration of 0.3 molar, because that's how much sodium acetate was added. And of course, we do have 0 for the H+, because the acid itself hasn't dissociated yet. Okay. So let's make our change line. We've got our minus x, we've got our plus x, we've got our plus x. Okay. So we've got 0.3 molar minus x, we've got x, and we've got 0.3 plus x. So you can kind of see that the main function of the sodium acetate's presence in the problem is just to supply the solution with some ions. It's not really there because the reaction between the sodium acetate and the acetic acid really matters. Both are going to dissociate in water anyway. A situation such as this where you have an acid or a base dissociating and then you have a secondary source of an important ion in that equilibrium is called the common ion effect, because you have that ion that is in common with both of the reactants, both of those initial sources. Okay, you got to think about this like Le Chatelier's principle. What happens when you disturb an equilibrium system by adding some product? In this case, it is a little bit different because our system hasn't made it to equilibrium yet, but we have disturbed the system from the way we would have normally calculated pH. Okay, so instead of just having the acetic acid going into water and dissociating, we have disturbed what that situation would have looked like. Okay. As a result, the ultimate effect will be similar. Adding sodium acetate, and thus adding more acetate ion, shifts the equilibrium to the left. Okay? It kind of makes sense. If you're adding some of this, it's going to shift the equilibrium in that direction. Okay? That's going to reduce the amount of H+ that we have, and this is going to directly affect the pH. The conclusion we can draw is that the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. Okay? In this case, our strong electrolyte is the sodium acetate, and the weak electrolyte is the acetic acid. So let's go back to our problem real quick. Okay, so here's our problem. Now that we have our icebox all filled in, we can look up the K value for acetic acid to find that it equals 1.8 times 10 to the minus fifth, and that gives us a law of mass action that looks like this. Ultimately, if you input our E line from the icebox, it's going to look like this. Okay. In this case, we can make the assumption, which gives us an equation that looks like that, right here. And then finally, this allows us to solve to get a pH of 4.74. Okay. This is similar to what we've been doing with that slight addition of that initial concentration of the acetate ion. By comparison, if we were just to do an icebox, I don't know why I said Xbox, with just the acetic acid in a solution without the common ion, we would get something that looks like this. Okay, so in this case, let me move this box out of here. In this case, we have the equation, but we're just assuming a dissociation with no original input of acetate ion. So we have a 0 and a 0 concentration. This gives us a normal icebox. Okay. We can solve this for our X value, we can solve this for our pH, and get a pH of 2.64. This is what the pH would have been if we didn't have that common ion put into the system. Okay? Remember before we had a pH of 4.74, which means that by adding in that common ion, we've decreased the dissolution of the acetic acid. Okay. This is the important sentence you want to kind of hold on to. The extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. That's the common ion effect right there. All right, let's do another problem. Okay. Calculate the fluoride ion concentration and pH of a solution that is 0.2 molar in HF and 0.1 molar in HCl. Okay, so you can see right here I've already written our equation up here, and I've already started to fill in the X box, or the ice box. I don't know why I keep calling it the X box. I've already started to fill in the ice box. We start off with our 0.2 molar HF, okay, and if we look up here, we've got 0.1 molar in HCl. Okay. The HCl is a strong electrolyte, so it's going to fully dissociate, which means that this entire 0.1 molar can be considered as 0.1 molar of the H plus ion as well, which means we're starting off with a little bit, okay, not just 0. So we have a little of the HF, we have a little of the H plus, we have nothing from the F minus because there's no other source for it, and we assume that this one hasn't dissociated yet. Okay. Write in our change line, fill in our equilibrium line, and that allows us to write our law of mass action with a K value that I looked up in a table. We can apply the assumption to this problem, and that's going to give us an X value of 1.4 times 10 to the minus 3. But the catch here is, because of the way the problem was set up, remember X right here is our X over here. So X equals our F minus concentration. So you have to be careful. You can't just take that and take the negative log of that to get our pH. We also have to put X into here to get our H plus concentration at equilibrium, and that's going to give us a pH of 1. Okay, so make sure you take the X, put it into this little equation right here, and that's going to give us our pH of 1. All right, one of the most common applications of the common ion effect, which was introduced, which we just introduced, is the idea of a buffer. A buffer is a solution that is generally made up of a weak conjugate acid-base pair that creates a situation in which it can resist changes in pH. Okay, so it's basically a system that can resist changes in pH imposed by outside influences. Okay? A great example of this is your blood. If your blood was affected by every acidic or basic thing that we put into our bodies, we would never have a stable system. Okay, so your blood actually acts like a buffer so that as you drink some orange juice or take in something into your system that has an acidic content or a basic content, you don't mess up your entire body's pH just by eating one little thing. Okay, So a buffer works because it contains both the acidic species to neutralize any OH minus ions and a basic species to neutralize any H plus ions. It's kind of like you have an acid and a base working together to neutralize any other acids or bases that are put into the system. The acidic and basic species that make up the buffer, however, can't consume each other through a neutralization reaction. Okay, so while you do have to have an acid and a base present, you have to make sure that they don't neutralize each other. Okay. As a result, one of the best ways to accomplish this is by mixing a weak acid with its conjugate base, or a weak base with its conjugate acid. An example of a good pairing is to mix acetic acid with the acetate ion. Okay, so you have the acetic acid, which would be our weak acid, and the acetate ion, which would be the conjugate base. Essentially, these problems operate just like common ion problems. Okay. For example, let's do a problem. What is the pH of a buffer solution composed of 0.5 molar formic acid and 0.7 molar sodium formate? So in this case, right off the bat, you can already see that we have a weak acid and we have a strong electrolyte that's going to provide a common ion to our weak acid, which means that we're already going to start off with a weak acid and its conjugate base. Okay. So what is the pH of a buffer solution composed of these two ingredients, these two reactants? Okay. Okay. So if we look at this, we can set up our ice box. Okay. And I'm actually just going to write that up here. We've got ICE. Okay. And we can start off by writing in our 0.5 molar here. Okay. We're just going to ignore water the whole way down. We don't have any initial source of H+, okay, but we do have a 0.7 molar initial source of the formate ion over here. Okay. So minus X plus X plus X. So fill in our ice box. You can see how a law of mass action could be set up for this. Okay, so up there on the top you can see that I sort of abbreviated the law of mass action. I looked up the Ka value in a table. I wrote the law of mass action. But remember that the ultimate goal for this is to get the pH. So really what you want out of this is the H3O+. Okay. So what we could actually do is we could take our law of mass action equation and we can solve it for the H+ concentration, which gives us this. Okay. Which is essentially the H+ concentration equaling the acid over the concentration of the acid over the concentration of the conjugate base, all of that times our Ka. Okay. Essentially, if you remember, in order to get from the H+ concentration to a pH, you have to take the negative log of it. So if we want to make an equation that is automatically going to get us from the original problem to the pH, we need to take the negative log of what we already have, of this equation right here. Okay. This gives us something called the Henderson-Hasselbalch equation. Okay. And it's basically taking the negative log of this equation right here and making it a little bit more useful for determining pH. It looks like this. Okay. You wind up with pH right here, pKa, the log of the conjugate base over conjugate acid, the ratio of those two concentrations. Okay. So if we were to actually go back and solve our original problem with the Henderson-Hasselbalch equation, it would look like this. So if you remember, what is the pH of a buffer solution composed of 0.5 molar formic acid and 0.7 molar sodium formate? There's our equation. If we actually just go ahead and plug everything into the Henderson-Hasselbalch equation right here, we get a pH of 3.89, which is what we would have gotten with the icebox as well. Okay? So essentially, you can use the icebox or the Henderson-Hasselbalch equation for these types of problems. Both ways of solving them work. Obviously, the Henderson-Hasselbalch equation is quicker, but the catch is, if you notice, it only works if you can make the assumption. Okay? If you can't make the assumption, you are stuck still doing the icebox. But if you look at the Henderson, let's go back real quick and look at that derivation. Yeah, if you look at the Henderson-Hasselbalch equation, it does rely on the fact that you can make the assumption. Okay? So it's awesome, it's great, it's good to use as long as you can make that assumption. But if you can't, it's going to get you into trouble. You do have to do the icebox. So icebox always works. Henderson-Hasselbalch works most of the time. You just have to remember that one time when it doesn't. You just have to be aware of that. Okay. All right, so just a little bit more about buffers. Okay. The first thing that you need to know about buffers is they should be able to control the pH. Okay. Actually, let's go back real quick. If you look at our Henderson-Hasselbalch equation down here, if you want a buffer to be at a certain pH, for example, blood should be approximately 7. If we want that buffer to remain at a specific pH, we can select an acid and base pair based on the pKa that acid is going to have. So you actually have the ability to adjust. And then, so you pick an acid that's got a pKa around the pH that you're going for. And then you can adjust the ratio over here to make sure you stay within that range. Okay, so let's look at that real quick. Okay, so that's controlling the pH. The other thing that a buffer has to have is something called capacity, which basically refers to how much of a strong acid or strong base you can add to an established buffer system before you affect the pH. So the idea is that once you establish a buffer system, you can add in a little strong acid or a little strong base, and you're not going to be able to change the pH because the system that's already there will neutralize it. But that's only going to happen to a certain extent. Eventually there's going to be enough strong acid that you add that you affect the pH, or strong base. Okay, so that's buffer capacity. Okay. And the third thing you need to know is that if you have a solution, a buffer solution, if you dilute it by adding more water in, all you do is change the concentrations of the two parts of the solution, two parts of the buffer, but you change them equally because you're diluting a whole system. So when you dilute a buffer solution, it's not going to change the pH. Okay. So that's a little bit about how the common ion effect is used, about what a buffer is, and about how to solve those problems. All right, now try these 3 exercises. Bring your notes to class, and we'll work on some problems tomorrow.